Great. Thanks, Jacob. It's been wonderful to hear from so many people who are passionate about Bayesian optimization and active learning. I'd like to talk to you about the critical commodity that they depend on, which is accurate data. So usually we get data by humans performing experiments. Unfortunately, humans vary in their experimental technique. They make cognitive errors. They have low throughput, and they don't keep great records. Robots, so self-driving labs, liquid handling robots, are a solution, but they're inflexible and they require a large upfront investment. And they can also make errors because they don't adapt well to conditions like variability in sample viscosity. Saddlepoint Labs is building computer vision-based cobots that act as a second set of eyes to address human weaknesses while also retaining their flexibility at a cost several orders of magnitude lower than a commercial liquid handling robot. So our computer vision system watches experimentalists perform procedures to alert the experimentalist to errors, to identify differences in experimental technique that create variability, to document work done, and to accelerate work by guiding the experimentalists during the procedure and helping them debug problems. The approach is flexible because humans still perform the procedure, and the upfront investment is much lower than a robotic system because a camera in a computer is 1,000 times cheaper than a reliable robot. So our initial focus is on manual pipetting because it's error prone, number one, and yet it's of critical importance in the life sciences. Most pipetting is still done manually. So here's a photo of our pipetting system on the bench in one of our pilot labs, the School of Chemical and Biomolecular Engineering at Cornell University, where I'm also a faculty member. So it's a camera mounted on a sterilizable 3D printed plate stand. So let me just show you here. I'm going to exit screen share. So it's a camera system, and there's a receptacle where you can put a microwell plate, and it positions the camera to be able to see what's happening. Thanks, Jacob. Um, Omer is going to go ahead and demo the pipetting system. Go ahead, Omer. Oh, and I think maybe you're muted.
Also noting, is this a live demo? Oh,
It's a
here
live
we go.
demo.
Amazing. Everyone hear me now?
Yeah.
Perfect. This is one of our procedures that we have where you can see in the top right, this is the camera stream that we get out of it. And so if I do some pipetting, you can see that if I go to engage in well A1, the system catches it and we have it. Um, and as I go about it, I am pipetting into an empty plate with a lot of volume, so I can look at the plate and see what I do. But oftentimes in pipetting, as I go into C3, um, you are pipetting a small, almost imperceptible amount of volume into a well plate that already has volume in it. So you cannot visually tell if you have already gone into this well or not. And the best method right now is just remembering. And as we all know, that is not ideal. Um, and another thing that we are working on is not just pipette tracking, which well you went into, but also if we can find errors in if we can find errors in how you pipetted. Either do you have bubbles or did you get the wrong volume? And so if you can see here, I just pipetted with a bubble in here. So if you see there's a little bit that goes in and out on the pipette tip, which is a bubble, which would cause you to get the wrong amount of volume than you expected. And so the first step in this task is to find the pipette tip in the frame. And so we are working on a segmentation model that can actually do that. And that's our first step in this error detection pipeline. Here, let me get this out of the way. And so we have been able to get accuracy as high as 99% with our pipette tracking system. And the next step forward is this um, planned procedure where, as if you can see on my screen, we one of the labs that we're working with as a pilot customer gave us their internal files so that we can generate a plan for them. And so if you can see on the well plate, there are some wells that are highlighted. Those are the wells that are intended for us to hit based on the plan that the lab uses. And so if I go to 8.4, it turns green to show that we succeeded. I'll go to B4 to show that it will hopefully succeed. And now I'm going to make a mistake. I'll go to C4. And then now we can see it doesn't turn green as is outside of the plan. This helps this helps lab techs go much faster as they don't have to constantly check back to their plan and then check what was captured to see if there was a discrepancy. We can allow them to move faster with fewer mistakes by showing them if anything went wrong. And so the last thing that I'll demo is we have a pilot customer that actually does this planned procedure with two plates where they're transferring from one to the other. And this is a diagnostics lab where you can imagine when you give blood, a lot of patients' blood will be in one plate, but then you're only running a test on a specific subsample of those plates, of those samples. And so you need to make sure that you are taking the correct person's blood for the test, because if you make a mistake there, you're going to give the wrong person the wrong test result, which would be obviously a large issue. And so to demo this, I'll start off with the first planned transfer, A4 to A4. I'll go from the source, and then I will go deposit it in the destination, and then the turns green on the left, and we have a check mark on the plan transfer. And then I'll start off again going from A6, which is the correct source. However, I'm going to now make a mistake. Instead of going to A3, I'm going to go to A1, which compromises the second plan transfer. And now the observed transfer gets marked a mistake, and both planned transfers A6 to A3 and A7 to A1 get marked as warning as they have been compromised. So if Peter, you want to take back over.
Yeah, thank you, Omer. So Omer showed our manual pipetting system, and beyond manual pipetting, we're working on a more generalizable system that uses cameras mounted in a biosafety cabinet where most of the important work in many labs happens. We're working on avoiding contamination, ensuring proper use of personal protective equipment, and tracking procedures in a general purpose way, integrating the data with a large language model interface used for debugging protocol issues. And we're also talking with a variety of labs about other use cases and sensing capabilities. We're a small company founded by myself and Nick Abbott. We're both faculty at Cornell. And we're currently beta testing our product at a small number of labs and are supported by non-dilutive funding from the US federal government. Please reach out. We're interested in hiring people with an interdisciplinary background for summer of 2026. We're also interested in working with new pilot labs that are interested in using our pipetting assistant. And we're also happy to discuss future projects, products, and potential collaborations. So thanks very much.